Once again, welcome to the Departments of Mechanical and Electrical Engineering Senior Design Project Presentations, Channel B. Our next group, Liberty Wire, with the advisor, Dr. Blair Allison, will be presenting. Team members include Damon Deck, Jonathan Douth, Chris Figuli, Alex Jozwiak, Caleb Miller, Austin Shank, and Samuel Worsham. The first speaker, please go ahead and do this.
Thank you very much, Dr. Klaus. Welcome, everyone. Thank you for making it to our presentation this evening. My name is Samuel Worsham. This is the Liberty Electronics Automatic Sleeve Label Applicator Senior Design presentation. This is a project in conjunction with Grove City College and Liberty Electronics in Franklin, Pennsylvania for the 2020 to 2021 academic year. Team members consist of myself, Sam Worsham, Alex Jozwiak, Jonathan Douthit, Chris Figuli, Damon Deck, Austin Shank, and Caleb Miller. And this project is advised by Dr. Blair Allison. So a little bit of background on this project. One of the main production items that is done at Liberty Electronics facility is the production of large-scale industrial wire harnesses. You can see a gentleman constructing an industrial wire harness on a board at the top left of your screen. Now, these industrial wire harnesses are sufficiently complex, plugged into large-scale machinery. And because of this complexity, individual wires in the wire harness need to be labeled. And these labels come on rolls of labels. You can see on the left-hand side of your screen a roll of such labels. This roll of labels comes on a strip of paper called a label carrier strip and has individual labels which are attached to an adhesive that can be peeled off and then popped open, a bit like a piece of penne pasta, and then stuck onto a wire. However, this process of wiring individual labels is very time and labor intensive. And so because of this, an efficient automatic application of these wire labels to construct industrial wire harnesses is desirable. And it is through this desire that Liberty Electronics initially approached Grove City College in 2020. You can see on the right-hand side of your screen, a gentleman manually applying wire labels. And on the left-hand side of your screen, the result of the spring 2020 independent study that was done in conjunction with Liberty Electronics. Now, this independent study was able to produce a digital prototype, though a physical prototype was not constructed due to COVID-19 disruptions. However, it did provide key design solutions that were later used in the senior project, notably the use of a tractor feed printer and vacuum forces, which will be gone into more detail later in this presentation. Because of the success of the digital prototype, Liberty Electronics approached Grove City College for the 2020 to 2021 academic year to turn this mechanism into a senior project. And with that, there were an addition of several other product design specifications. And you can see those listed on the left-hand side of your screen. Notably, we were tasked to create a mechanism that can remove a wire label from a label carrier strip and then place it onto a wire. That mechanism should be capable of moving the wire label carrier strip into position, removing the wire label from the label carrier strip in whatever order of operations was deemed most appropriate. And that this mechanism should be controlled by an operator, specifically with the machine cycle being initiated by the operator pressing a foot pedal, and that the operator should be alerted by the mechanism when it is time to insert the wire into the open wire label. And specifically in terms of application, this mechanism should accommodate 2-inch long, 1/8 inch, 3/16 inch, and a 1/4 inch diameter sleeve labels. You can see a picture of those labels on the right-hand side of your screen. Now, just to note, these labels are larger when they are laid flat on the strip of paper. However, when they are removed from the adhesive and popped open, they do acquire that diameter. So this project was initially in the fall semester was mainly design, and then in the spring semester was the construction and testing of the mechanism. You can see here the results of that construction and testing. and the front part of the Liberty Electronics automatic sleeve label applicator, or LESLA. You can see that the main body of the mechanism is on the cart with a electrical subpanel mounted on the right, with the main mechanism frame to the rear of the cart. Now, this mechanism frame is about the size of a large sewing machine, with dimensions by 33 by 8 by 14 inches. You can see on the back side of the mechanism, on the left-hand side, you see the pulley system that is used to move the tractor feed, which will be gone into more detail in a bit. And you see on the back side of the mechanism, the door, which is open to then access the inner workings of the LESLA. So just to go through a bit of the general process with how the LESLA works. So first, the wire labels on the label carrier strip are inserted into the mechanism. Then through the LESLA sub-mechanisms, the motors and vacuums open up the wire label. It is at this point that a indicator on the HMI alerts the operator that it's time to insert the wire. Then the operator inserts the wire into the open wire label, and as the mechanism is waiting for the foot pedal during this time. The operator will then press the foot pedal, and then the motors and vacuums of the mechanism reset as the operator removes the wire label assembly from the mechanism. It is then at this point that the tractor feed moves on to the next label, and the process continues, with each iteration of the process being started by the operator pressing the foot pedal. So I will now go on to Alex, who will go into some detail of the individual sub-mechanisms in the LESLA.
Thanks, Sam. As Sam said, I'm going to start discussing some of the mechanical subsystems. First, here we see the carrier strip holder. This is where the inserted labels are stored before they're fed through the assembly. The holder was designed to have a carrier strip either wrap around it or hold an entire roll as it unwinds with the labels being removed. The holder is held up with mounts that can be tightened and released on the turn with the turn of a handle to allow for easy replacement of the carrier strip. Then on the right is the alignment bar, which lines up the carrier strip to the removal mechanism that we will see on the next slide. The removal mechanism starts with an air cylinder engaging and clamping the carrier strip between two plates, with one of them being stationary. The air cylinder continues to move up and uses its bottom stamp to begin to remove the label from the carrier strip. As it moves up, it meets another stamp, clamping the label in place. Then a linear stepper motor retracts, allowing the label to be opened and a wire inserted into the label. On the next slide, we'll see the stamps that clamp the label to be opened. These stamps have complex geometry in order to fit into the smallest label hole on the carrier strip and hold the vacuum gripper system, or VGS. The VGS consists of vacuum cups and fittings that allow the cups to grip the surface of the label and keep the label in place once it is removed from the carrier strip. These cups are designed to work on the smallest label size, but work on the biggest label size as well. Since these stamps only have vertical movement, the carrier strip must be aligned with them. So the next slide, we start to look at the movement system. Here we can see how we're determining the alignment of the labels with the stamps. A fork sensor in the red oval is mounted before the tractor feed, and it determines when the trailing edge of the rectangular punch in the carrier strip is hit. This rectangular punch can be seen in the purple oval, and in the red dot the fork sensor uses to find this edge can be seen in the blue oval. Once this edge is found, the stepper motor advances the carrier strip a set number of steps to align the next label. This fork sensor controls the motion in the tractor feed on the next slide. This is the tractor feed. It's being used to move the carrier strip. This carrier strip has holes along both sides that are ½ inch apart and are standard on all different size wire label carrier strips. These holes are pointed out in the red oval. The tractor feed utilizes these holes by having pins that extrude out of the belt that fit into these holes to allow the tractor feed to grip the carrier strip. This tractor feed was placed as the last step in the assembly due to the carrier strip being flexible. It was determined that it's easier to pull the carrier strip through the assembly compared to trying to push it through, which leads us to the movement of the tractor feed on the next slide. So the motor that drives our tractor feed is just a basic stepper motor. The motor is attached to a shared support bracket with the tractor feed and can be seen in the blue circle. The axle attaches to a timing belt and pulley kit on one side and the square driving axle of the tractor feed on the other. These pulleys are held in place by using set screws in the hubs to allow the timing belt to provide enough torque to the square axle to drive the carriage strip. And now we will hear the electrical overview from Damon on the next slide.
Thanks, Alex. My name is Damon Deck, and I primarily focused on the electrical side of the project. So first, I would like to introduce two of our main components that we used in the control system. And this is the PLC and the HMI. So the PLC is depicted on the bottom right picture. And PLC stands for Programmable Logic Controller. And this is programmed in a programming language called Ladder Logic in a program, Studio 5000. We see an example of this programming language on the top picture on your screen. And this was one of our main problems or our learning curves that we had to do over the semester. So Caleb, Austin, and I spent most of last semester learning how to implement this unique style of programming into the PLC. The PLC is just basically the brains of the system. So we use this ladder logic to program this PLC, and then it tells our motors, it tells our vacuums when to turn on and off, and so forth. Also, another big component of our project was this HMI component. The HMI stands for Human Machine Interface, and it's exactly what it sounds like. So it's basically a small screen. It's a touch screen, and we developed some menus and some screens to interface with the machine. So basically, it tells the user some important information about where the machine is and what it's doing. On the next slide, I'm going to go into a little bit more detail about these screens. So first, when you walk up to the machine and you want to apply a label to a wire, you're going to be presented with this home screen, as you see on the top. So there's a few different options that you can press. First, let's start on the right side. We can press the start button, and this initiates our sequence of options and our sequence of events that happens to remove a wire. So in this run screen, so if you press that start button and you're going to another menu screen, this is the run screen. We have a few things here. We can see the pedal status, and we can also have an indicator for the door or the e-stop error. These are just a few indicators to see what the machine is doing. Also, we can see the machine status, so we can see if it's stopped, if it's waiting for a pedal, if it's running, or if it's resetting. This is just a good information that the operator might use. So if you hit that return button, you're going to go back to the home screen, and once this, you have a couple of different options. You have the change label size. The change label size, you can go from your different size of labels, and then another option from the home screen. You can also load or eject the label roll. This is basically just turning the motor in one direction. So if you wanted to load the roll, you would move the motor in a forward direction. If you wanted to eject it, you would just reverse the motor. And then next, I want to talk about some of our solenoid control. This was one of the main components that we decided to implement in our project. This is what distinguishes our design. And a solenoid is basically an electrical device that directs the flow of air. And this controls our vacuums. This turns on and off our vacuums, and it also powers our cylinder that moves that clamping system up. And one important thing to note about these solenoids is that they take a different current than our PLC current, that are control current. So we had to put a relay in between our PLC and our solenoid. So our PLC delivers 24 volts to the relay at a lower current, and then the solenoid on a second circuit is able to be actuated by that relay being triggered from a digital output given by the PLC. So this is how we control our solenoids, and this is how we divert this pressurized air to our system. Next, I would like to talk about our motor control. In industrial motor control applications, we discovered that this process takes about 4 steps to get accurate results. So first, we program, like in that ladder logic that I mentioned before, we have a few function blocks, that's what they're called, to move a motor either a certain distance, or we can just turn them on and off. So the 2 functions that we decided to use for this project was a jog function. This simply turned on and off the motor, and we were able to use this. That's in the load and eject mode of our HMI screens. And then also we had an absolute move function. So this turned the motor a certain set of degrees or steps. And this was crucial to get the proper amount of accuracy in aligning our labels to our clamp system. So then from the PLC, this signal gets translated by a motor controller, and then the motor controller sends a pulse output to a motor driver. And again, these motors, this NEMA 17 and Axionis S20 linear actuator, they're both stepper motors. They both require a different current than what is supplied by the controller. So that's why we need a motor driver in between our controller and our actual motor. So again, the process goes, we start programming in ladder logic. We put those functions in. We either call a jog command or an absolute move, and that's in the PLC. Then we move on. Then it gets sent to a motor controller, and then we have a motor driver once again to provide the correct currents for that stepper motor, and then that gives us our turning. That gives us our rotation. And so finally, we have all of these components combined together. On the right, you see the electrical panel. It's all neat and organized, and it's all labeled. And this is super important for troubleshooting. And if anything goes wrong, or if a component needs to be replaced, it's nice and easy to access. And then on the left, there's our final schematic. This is everything combined. Our motors, our drivers, our relays, our PLC. We have 2 power supplies, a fork sensor, all these things combined. And this is a good reference to have if any troubleshooting needs to take place in the future. I will now pass it on to Chris, who's going to talk about some of the mechanical troubleshooting that went on during the semester.
Thank you, Damon. I'm Chris Sigley, and I'll be talking about some of the problems that we had this semester and how we ended up fixing them. The first piece that gave us the most problem was the embedded piece. It's the part of the mechanism on the bottom half of the vacuum tower that connects the air cylinder to the bottom stamp. When we first designed it, we didn't give it enough room to move up and down freely, so we ended up taking an 1/8 of an inch off either side of it so that it could move up and down. We also redesigned the holes on each of the 4 towers you can see on the top right picture to allow these springs and the dowel pins that are set within the embedded piece itself to squish between the embedded piece and the clamping part of the mechanism. The next problem that we ran into was the tractor feed mounting plates. When we first designed mechanism, we measured the hole distances that the axles sit in to be just slightly too close together. So we ended up having to slot out one of the holes where the stationary axle sits in, so the tractor feed could move freely. Another problem we ran into for the servo motor driving pulley system, one of the hubs that connects to the square axle of the tractor feed was rubbing against the bolt that was set in the tractor feed plate itself. You can see in the top right picture, circled in yellow. We 3D printed a small piece that separates the plate from the hub to keep the hub from cutting into the bolt and cutting a small groove into it, possibly causing the tractor feed to skip or the servo motor to skip or miscalculating the steps or angles that it's driving. Another problem that we ran into was in our measurements of the stroke length that we needed to provide for the system. We miscalculated the linear servo motor stroke length and the top stamp distance, so that it was not far enough to reach the top of the carrier strip. So we increased the top of this top stamp a half an inch. You can see our first design on the bottom left for the top stamp by half an inch. To allow it to reach the carrier strip, and the bottom stamp to allow it to clamp together. Lastly, during testing, which Jonathan will talk about later, we noticed that when we inserted wires into the labels, it would push the wires off of the suction cups, causing it to fail, not open up the label all the way enough. So we designed and 3D printed backstops. You can see in the bottom right picture, there's our final design of one of the backstops. This is for the 10 gauge wire. It's the 10 gauge wire along with the 1/4 labels proved difficult because with the distance that they are opened, and the width of the 10 gauge wire itself would cause the wire to fall off of the suction cups. I'll now hand it off to Austin to talk about the electrical troubleshooting.
Thanks, Chris. So after the mechanical aspects of the project were running a bit more smoothly, we still had some electrical and control issues that we had to iron out. And one of the big ones was that our PLC was issuing the correct commands to the motors to move, but then the motors maybe every like 50 runs or something like that, they just wouldn't run for some reason. And this wasn't a big deal because we could go into the code manually and reset the controller, and it would work from then on. But we didn't want an operator to have to go into the code every 50 motor turns or something to reset it. So we put a lot of work into making the PLC to actually detect when the motor was supposed to be moving, but it's not, to catch those errors and failures, and to reset whatever it had to on its own and fix it. So by the end of the testing and development process, every error we've encountered, the PLC can now do what it needs to reset it and carry on without the operator even knowing. So we also had to incorporate some safety mechanisms, mainly that is the emergency stop button. This is to be used whenever, if something gets jammed, something gets caught, something doesn't work right for any reason really at all that the operator wants to stop the process, they can press the emergency stop. So when this is pressed, basically it cuts all the vacuum, it cuts all the air, it stops the motors, so nothing, if something is pinched, nothing is pinched further. And yeah, and when the mechanism even loses power altogether or air, the same thing happens. So that's the way we designed it. So when it loses power, everything stops, the air stops, just to be as safe as possible. And we also have a switch on the back of the machine that is triggered if a door is opened in the back, and that also just does the same thing. It stops everything. So we tried to cover all our bases there with safety, try to keep everything fairly safe. And at this point, we could start running labels through consistently and get good results and be pretty efficient at testing, which Jonathan is going to explain and summarize next.
So we began testing the vacuum cups on February 2nd and demonstrating the opening capability of each label, given the positioning of the vacuum suction cups. These tests were an indication of the ability of the suction cups to open the wire label and the impact of misalignment on the wire label opening. Looking at the graph on the left-hand side of the slide, you can see our results of this early testing, which proved that the closer the cups were towards the middle of the label, the further the label could be opened. For the 3/16 inch labels, we were easily able to open the label 0.24 inches or more with proper vacuum placement. After the mechanism was partially constructed, testing was done on the mechanism on February 9th to determine if the appropriate wires for the label could be inserted. To pass this round of testing, the label had to stay connected to the vacuum cups until the wire was completely inserted. The results of this test yielded mixed results for the different sizes, as you'll see in the future slides, causing us to reevaluate how we are opening the labels and any modifications we can make to increase the reliability of our mechanism. Thankfully, our testing proved that the mechanism could function perfectly for the 3/16 inch labels. As you see on the right-hand graph on this slide, the test resulted in high reliability for the insertion of appropriately sized wire for the 3/16 inch diameter wire labels. However, testing of insertion of the wires proved problematic for the 1/4 inch wire labels and also the 1/8 inch wire labels, as you'll see in the next slide. Our conclusion from these tests was that our high failure rate may be due to friction caused by the wire label surface interacting with the wire. The friction pushed the wire label off of the vacuum cups before full insertion could be accomplished. In the slide here, you can see that although we were able to open the 1/4 inch labels farther than 0.2 inches, our test for insertion would fail for the larger gauge wires. Specifically for the 10 gauge and several runs of the 12 gauge, the opening would not be wide enough to insert the wire fully, and the vacuum force was not strong enough to maintain its hold on the label as the wire was being inserted. The issues recognized in testing the largest labels worsened when testing the 1/8 inch labels. Close to perfect alignment was required to open these labels at all, as shown on the chart on the left. Similar to the 1/4 inch labels, there were issues with inserting the wire due to friction and how difficult it was to properly open the labels with the tight alignment requirements. Since the 20 gauge insertion worked 4 out of 5 times, we hope to modify the mechanism in some way to allow for the labels to open further or to reduce the frictional force. It was due to this testing that the idea of backstops was implemented into the project, which Chris discussed earlier in the modifications section. The final testing of our mechanism occurred over the months of March and April after the full construction of the mechanism and integration with the automatic PLC control. Each size label roll was loaded onto the mechanism and 30 labels were removed and applied to simulate its use in a production environment. All the labels had 100% reliability rating for both positioning and removal from the label carrier strip, though the results were more mixed in the following stages of the machine cycle. As you can see in the slide here, the 3/16 inch diameter wire labels proved to be the most reliable of the 3 label sizes, with an opening insertion failure of only 1 out of the 30 cycles. The largest diameter wire label was the second most reliable, with a success rate of 86%. And the smallest label had an opening insertion rate of 0%. The 1/8 inch wire labels failed constantly because the top vacuum cup could not make adequate contact with the top surface of the wire label. The 1/4 inch diameter wire label failed occasionally because the wire label slid off of the cups and lost contact with the vacuum suction cups during the wire insertion process. Although the mechanism was proved to be incapable of applying the 1/8 inch diameter wire labels with its current vacuum setup, modifications would improve this performance, as Caleb will discuss here in the next section.
Thank you, Jonathan. So hello, my name is Caleb Miller, and I focus primarily on the programming and user interface aspects of this project. But here I'm going to discuss some of the future recommendations that we had going forward. So as shown in Jonathan's testing slides above, we had some issues opening the smaller labels correctly. One possible way to fix this would be by using more vacuum suction cups. So currently we're only using 2 vacuums, one below and one above each label. However, the vacuum cups we ordered are only 12 millimeters long, and the labels are a full 2 inches long, which comes out to 51 millimeters. This means that technically we could fit up to 8 vacuums, 4 on the top side and 4 on the bottom side of each 2-inch label. This would provide more force and would create a greater opening for the wire to be inserted into. And this modification would in all likelihood significantly increase the success rate for opening the smaller labels. On the next slide, you will see that one stretch goal that we had that we are unfortunately not able to tackle this semester was cutting the 2-inch labels in half to create 2 separate 1-inch labels. Simply put, we did not focus too much attention on this goal given our short timetable. If more work were to be continued in the future on this project, one possibility would be installing some sort of knife or scissor mechanism between the spool and the vacuum mechanism. This open area is designated by the circle in red on the right side of your screen. And if we were to cut these labels in half, we would most definitely implement our previous recommendation of using multiple vacuums. After cutting the 2-inch labels in half, we could implement 4 vacuum cups on the top and 4 vacuum cups on the bottom of the label. Thus, after the label was cut into 1-inch sections, each cut in half section would still have 2 vacuum cups on the top and 2 vacuum cups on the bottom. And then if we were to have the cut in half sections, we could insert 2 separate wires into the 2 1-inch labels. And finally, I'm going to turn it back to Sam Worsham to finish off the project with our conclusion. Sam, I believe you're muted.
My apologies for that. So in conclusion, though future work is required to acquire the 100% functionality and reliability on the LISLA, we have proved it to be an effective method of removing wire labels and then allowing for operator control. And we think that this project very much provides the groundwork for innovations in efficient, professional-grade assembly of industrial wire harnesses. So in conclusion, thank you very much, and we will now take questions.
Obviously, there was a lot of startup learning when it came to the programming and controlling piece. But let's talk about maybe some soft skills, because those are going to be really critical in your future. And so what maybe soft skill did you actually learn more about while working as a team on this particular project that you would never have guessed from just taking coursework?
And Sam,
All right, I can speak to that a little bit. Certainly delegation. I was the project lead for this team, and just being able to split up the work between team members and just kind of collaborating to figure out who's going to work on this subsystem, who's going to work on this subsystem, and who's going to write this document. Definitely figuring that out and just kind of working with others. That was a soft skill I was very much able to develop, as well as the other team members on this project. Just because there were so many different things that were involved in creating the LISLA.
Yeah, and one thing for me that I noticed was I had the opportunity to work with some of our vendors on this project. So 80/20 from SunSource, I got to basically develop and help them design the frame. So that was really cool to work in combination with them.
Hi, this is Blair Allison. Question for you guys, Jonathan and others that were involved in the testing. When the operator, which in this case were the team members, when you're inserting the wire in the label, I would assume that the alignment of that wire with the label is critical. To what extent is success in wire insertion dependent upon the skills of the operator who's pushing that wire inside the label?
Yeah, so we did have a 3D printed part that was kind of a wire guide that's mounted on the outside frame of the mechanism. So that kind of like helps the operator guide the wire into the actual label. So there isn't too much skill required on that part. It's pretty much just grabbing a new wire and putting it through the wire guide. I don't know if any of the other teammates have any comments on that.
Yeah, for the 3/16 label, at least, it seemed like we could kind of just like shove the wire in there, like any which direction, and it would just work. With the 1/4 inch label, it was a little harder, especially with the larger diameter wires. Yeah, and then with the 1/8 inch label, we didn't have a ton of success, but yeah, at least with the 3/16 label, it works pretty well.
Mm-hmm.
Definitely, there wasn't too much opportunity to move around in the machine workspace, but definitely avoiding any considerable lateral movement would definitely be desired for an operator. But just to be mindful of that, but it's not something that you need a ton of training for.
Mm-hmm. Great, thank you.
Hi, this is Jay Miller. Question about the speed of operation. So for the labels, when it was working well, how many labels per minute could you do roughly, and how would that compare with the speed of doing the labels manually?
I can take that, Sam. So originally, one of our goals was having it in 2 seconds as a full cycle time. Unfortunately, we're more focused on the reliability aspect. So the current cycle time, which has some pretty precise movements, is currently 16 seconds, which is definitely longer than the target time. So if we were to consider some further work on this project, one area of concentration would be removing that, making that number less, which I do believe would be fairly possible to at least make it to 5 seconds or so. As to the manual operation, I'm not quite sure if Sam, you might have a better gauge on how that might.
Yeah, so manual operation through testing that I did when this was an independent study takes about 10 seconds. So definitely optimizing that time is something that we were not able to address too much, unfortunately, because we were focused on that reliability. That would definitely be another future recommendation for further developing the WESLA.
Great, thank you.
You may have talked about this because I've been trying to switch back and forth between a couple of presentations, but the idea of automating it the whole way instead of requiring someone to insert the wire, would that be something that you have thought of and left room for, or is it something that what are the reasons that first you didn't address that, and secondly that what would be required in order to add it in?
I can speak to that. So yeah, that was actually one of the project goals for the independent study, was to integrate it with other machinery. However, that wasn't really a focus this semester. A big challenge of that is basically integrating with other machinery would mean to modify existing machinery to accommodate for the WESLA, which is a bit of a challenge because that does involve proprietary software. However, that is certainly possible as a future development. I just wasn't super focused on too much this semester, or this academic year, I should say.
Makes sense. Thank you.
I have a question. You focused on some proposed new designs for your vacuum pickup. How much work did you put into sizing perhaps the original vacuum pickups that you actually used on your equipment?
Yeah, I can talk about that a little bit. So I did a lot of the vacuum and the vacuum force stuff earlier last semester. So the difficulties with it was we had to find a cup that would work for all 3 label sizes. So that narrowed down our possibilities. And also we needed something that was pretty narrow compared to like a lot of cups that were on the market. We talked to PIAB, which is one of our vacuum cup suppliers at the college, and they didn't really have anything small enough for what we were looking for. So we pretty much just checked out a couple other suppliers online. We ended up finding this German manufacturer that had oval cups that were small enough for a 1/8 inch label. If we weren't doing it small enough for the 1/8 inch label, we could have scaled up our vacuum cup. So it would have been easier to find one at a larger size, but since we had to get one small enough, it was a little bit difficult to find one that size.
Liberty Wire Group, thank you so much. We applaud you and hope you have a wonderful evening.